So now we want to talk about sigma and pi bonds. It's very simple to determine how many sigma and pi bonds there are in a molecule. We want to talk about that and then a little bit more about what it means to be sigma and pi. But first let's just kind of define a very simple way of figuring how many we have. So a sigma bond is the first bond between any two atoms. The first bond between any two atoms. And normally there's only one bond between two atoms, and so that's all you have is sigma. The pi bonds are the extra bonds. I'm just going to put extra in kind of quotes because that's not really what we call them, but that's what I'm going to use right now just to help explain it. Extra bonds between two atoms. Okay, so let's look at this molecule that I already put on here. And I'm going to kind of point out all the sigma bonds. So we have 1 sigma bond, 2 sigma bonds, 3. Remember, the first one between these two carbons will be a sigma bond. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So we've got 11 sigma bonds. So 11, and here is the Greek letter sigma. You can write it out, and spell it in English S-I-G-M-A, or you can just write the Greek sigma symbol. So we have 11 sigma bonds. And then extras. Well, there's 2 places in this molecule where we have extra bonds, and so right here we have an extra bond. The second bond that's between those 2 carbons is a pi bond, and over here on this carbon-oxygen double bond we also have an extra bond. The second bond is a pi bond, and so we have 2 pi bonds. And it is that simple. All you do is count the first bond between every 2 atoms, and that's sigma. Then you count anything extra, like a double or a triple, and you have that as your number of pi bonds. So what is the difference really between a sigma bond and a pi bond? Now that we know how to identify them and find them, let's figure out what they are. If I have a carbon and a carbon here, so I have 2 carbons, and this carbon, let's go into a little more detail about this. Look up at this carbon above where I'm circling the double bond. This carbon, each of the carbons actually, is bonded to 3 things, right? It has electrons going in 3 directions. And if we have 3 electron groups, we know that the bonding is sp2, right? Or the orbital is sp2 that it's going to use for bonding. So here I've got, on this carbon, I've got an sp2 orbital coming out like so, and the little lobe that we usually don't draw in behind. And then I've got another sp2 orbital coming out like so, and the little lobe that we're coming out behind. So we have sp2 and an sp2, and they're going to overlap, and what we're going to get is something like this. Our 2 carbons, and we're going to get orbital that's more like this with 2 tiny little lobes in the back that everybody kind of ignores. So this is going to be our bonding orbital for the 2 electrons. So notice that if you were to draw a line between the 2 carbons, that bonding orbital for those 2 electrons would be right around that line, around the axis that joins the 2 carbon atoms. So this is our sigma bond. So there's our sigma bond with 2 electrons in it. So we could even just put in 2 electrons if we wanted to. There we are. Now, if we're going to put in a double bond, well, how much have we used? Let's see, if we had s and 3 p orbitals and our 5 ds, which we can't access because carbon is a second period element, so it can't use those at all, so we're not going to use those. But what we've used to make our bonding orbital there is we've taken 3 orbitals. We've taken an s and a p and a p, and we've made sp3. But what about the guy that's left over in the p? Here, this guy here, that p orbital is just sitting out there empty. No electrons in it. We used 3 different sp3s for bonding to the 3 atoms that the carbon's bonded to. The other carbon, and then like this end, if we go back up to our original molecule, this end, it has also a hydrogen and a hydrogen. So our 3 sp3 orbitals are occupied. But I've got this empty p orbital that hasn't been used, and it's just sitting here, and each of the carbons has one. So what we're going to do now is we're going to kind of lean those together. So I'm going to kind of let them lean towards each other, kind of like that. Okay? And, well, it's actually, I'm not drawing it in perfect perspective. They're actually kind of fatter and closer to each other. So what we end up doing is forming kind of a thing that goes like this on top and bottom. So that's kind of a cluttered drawing. So let me kind of redraw that. We've got our sigma bond like this, and then I've got kind of a pi orbital up here and a pi orbital up here. Lobe. Sorry, lobe. This is one lobe. Okay, so 2 lobes equals 1 pi orbital. They are not 2 different orbitals. They are both part of the same orbital. Just like if the sigma bond was a sausage, like, you know, your bratwurst, and you were putting a bun around on it, you would have 2 halves of the bun, but that would only be one bun. You would have the top half of the bun and the bottom half of the bun. And so the 2 lobes together make one orbital, and 2 electrons can go in there. So we have 2 electrons in the sigma, 2 electrons in this pi orbital, and that is your double bond. Now, what if we have a triple bond, where there's 6 electrons shared? And I'm going to try to, this is kind of hard to draw, but we're going to try. This carbon's kind of behind this one, so see, I'm going to draw this kind of, there's my sigma bond. All right? So then I have up above, I have the, and below, I have the 2 lobes of the pi orbital. Okay? That's the second bond. And then, this is, going back to the sausage analogy, we have the sausage, we have the bun on top and on bottom that makes 1 pi orbital. This is a really carb-loving situation here where we say, okay, that's great, I like the sausage, I like the bun, but I really like the bun, so I want more bun. And so what you do is you put on another bun on the sides, and this one's kind of hidden back behind there. And so to the left and right. And so looking down the axis of it, if you were looking straight at it, your carbon with your carbon kind of hanging out behind, you couldn't really see. There's a carbon and there's a carbon. You would have the pi orbitals would be arranged kind of like that. This is a pretty lousy picture. Forget that part. I can't draw it 3D. It's really nice to have a 3D model at this point. But the main thing is that you have the sigma bond that is on the axis. It's stronger because it's on the axis between the carbon and carbon. And then the pi electrons are kind of sitting out there to the sides, and they're a little easier to react with, and so that makes pi bonds fundamentally different. They're more reactive than sigma bonds. And then if we put yet a third bond on, it'd be to the front and to the back of this sigma bond here. Okay, so hopefully that helps with sigma and pi bonds.